Hello, and today we're going to be talking about definite integrals. We already set the stage for this a little bit by learning how the indefinite integral works, but today we're going to combine that knowledge with what we've already figured about area via rectangle approximation or what have you. So the whole idea behind this is that this cool thing we've been doing with antiderivative and calculating the integral is actually the exact same thing that we've been doing with the RAM, the rectangle approximation. The only difference is the integral allows you to essentially have an infinite number of rectangles. So if we try and approximate under the curve with an infinite number of rectangles, we can get a pinpoint accurate answer instead of the approximation that we've been getting via RAM. To do that, we're going to play around a little bit. We're going to play around a little bit with GeoGebra and see how this stuff might work together. Here you see the shaded region, and our area is 7.33. Starting at -1 and going to 1, that's the area under this curve, 4 minus x squared. If I move the b over a little bit, I can see that I can get a bigger area of 9. And as I keep going, I actually see that number start to go down. Areas above the x-axis are treated as positive, and areas under the x-axis are treated as negative. So as I take b all the way out to the edge, I get that number. If I take a all the way back, I can actually get an integral of 0. So you got to be careful. Integrals can be positive above or negative below, whereas obviously this does not have an area of 0 because that doesn't make sense. I can see I wouldn't need 0 buckets of paint to paint this because it's above and below. So be careful the difference between the integral being positive or negative and the area always being positive. One way you can fix that is by playing around with order. If you put a at 3 and then b back at, -1, you can see that I actually end up with a negative result. The reason being, if my a value is larger than my b value, it actually takes the answer and flips the sign. So going from high to low actually produces a negative integral, as does going down below. So if I try and set my b to this intersection, and I set a all the way out there, even though this normally would be a negative integral because it's under the x-axis, I flip the order, and I'm going from the high value of 4 down to the low value of 2. So the double negatives actually produced a positive integral. Saying that one more time. Below the x-axis would produce a negative integral, but going out of order and having a bigger a than b, going from the high number on the bottom to the low number on top, actually also produces a negative. So the two of them work together to make a positive value. So negative, positive. So what's that got to do with anything? Well, first off, it's probably a good idea to review the RAM stuff we were doing before, just to make sure that you really have that stuff down. And heck, it wouldn't be such a bad thing to have a video of that. So here we have a curve. We've got 1 plus 2x, so you know it's going to look something like that. Starting at 1, and I want to go to 3. It's going to create this trapezoid-looking shape here on the inside. Just to add a little bit of color to it, let's make it yellow. We're going to try and find the area of this yellow trapezoid shape. How are we going to do that? We're going to do that via RAM sub 4. So the first thing I might want to do is figure out my delta x. My delta x is the high value 3 minus the low value of 1 divided by the n rectangles I'm going to be using. So my delta x is going to be 1/2, meaning that the width of each one of the 4 rectangles I'm going to draw is 1/2. So starting at 1, I come 1/2. Then I go to 2, then I come 1/2, and then I go to 3. Each one of these rectangles is going to hit on the right-hand side. So this should be the top right-hand corner of my rectangle. This is going to be the top right-hand corner. This is going to be the top right-hand corner, and that's going to be the top right-hand corner. So my first rectangle has a width of 1/2, and it has a height of whatever I get when I plug 3/2 into the equation. 3/2 into the equation is actually going to give me a y value of 4. The second rectangle, I'm going to plug a 2 into the equation. When I plug a 2 into the equation, I'm going to get 5. Then I'm going to plug 5/2 into the equation. And when I plug that in, I'm going to get 6. How convenient. And when I plug 3 in, I'm going to get 7. Add all those up, and that's going to be my answer. So that is the area under the curve. Really, the only big surprise here is that putting little numbers, a's and b's, on my integral symbol, and that's giving me the exact area. I'm approximating this exact answer using rectangles. Alright, so pretty much the same thing again. This one's going to be 2 minus x, which is going to be a slightly different curve. I'm going to start at -1, and I want to go to 3. LRAM sub 4. So again, I'm going to figure out my delta x. 3 minus -1 over 4. And I'm going to realize I have a width of 1. And this time I want LRAMs. So that's my first guy. That's my next guy. Third. My fourth ends up being flat on the axis. So pro tip, if we were doing RRAMs here, you could actually have that rectangle that's dipping down below be a negative area included in your answer, depending on whether or not you wanted the integral or you wanted the area. All right, so this first one looks like it's going to have a height of 3. This next one's going to have a height of 2. This third one's going to have a height of 1. The last one has a height of 0. Remember, a good double check is that I have 4 things here, and I have LRAM sub 4. So that's a good sign that I'm doing it right. And we find out that our approximation is 6. Okay, that's all well and good if we have pictures and we're actually counting things out, but let's talk about the theory of how these things work. We've got a couple different rules that go together for definite integrals. You know you're dealing with a definite integral when you have numbers on the squiggle. These numbers let me know that I'm dealing with a definite integral. I'm getting a numeric answer for the area, as opposed to an indefinite integral, which means I'm just trying to get the antiderivative, a general equation. If I'm going from a to a, that basically means that I want 0 space under the curve, so the answer is 0. This can often be a trick question. If you're looking at a definite integral and the equation looks hideous, double check your bounds. It could just be that I'm trying to be sneaky. If you go from b to a, that's the same thing as going from a to b with a negative out front. Flipping the order of these two bounds causes the answer to be the opposite sign. This one we've used a whole lot. It was very popular in substitution. A constant inside the integral can be moved out front. This last one is very intuitive if you look at a picture. Looking at just the words, probably it's not all that strong. If we start at a and we go to b, if you add a little c value in between, this rule is saying that from a to c, this first integral, plus from c to b, the second integral, is the same thing as going from a to b. If you remember that integrals represent the area under the curve, that's very logical. I'm saying that this area plus this area adds up to the whole thing. I think we can all agree on that. All right, so let's try it. For these problems, they tend to be very theoretical, and sometimes that can make them tricky. Somebody has gone out and measured for you. Underneath the function f of x, between 2 and 7, they found that the area is 5. I don't know, I guess you had an intern or something like that, and they went out and they measured this for you, and you definitively know that that area is 5. You also know that the area under the g function, between 2 and 7, is 10. Our job is to try and calculate this. Now the cool part is that integrals can basically distribute just like regular numbers. So we can take this 7 to 2 and distribute it to the first piece. It gets its own dx. And we can distribute it to the second piece. And it gets its own dx. If you want it to, you can pull this 8 out front of the integral. And you can pull the 4 out front. Do it in your head. You don't actually have to denote it if you don't want. And let's see. The integral of 7 to 2. Well, that looks an awful lot like this one. The only difference is the order's wrong. I know that from 2 to 7 is positive 5. So from 7 to 2, which is my upside down rule, that should be negative 5. Same goes here. I know that 2 to 7 is positive 10, so 7 to 2 upside down should be negative 10. And I'm going to get myself a negative 40. Minus 40 is negative 80. So my integral for this problem is negative 80. My area might be 80 or it might not be 80 depending on how it plays out, but my integral is negative 80. All right, so here we're looking to merge. This 2 to 10 is basically saying that if you have this graph, you have some kind of thing going on. Between 2 and 10 is this first integral. It's this whole chunk underneath the graph. This symbol represents all this region. If you take this region and you subtract out the portion from 2 to 7, they want to know, what are you left with? Well, if you take 2 to 10 and you subtract out 2 to 7, all you're left with is this portion right here, from 7 to 10. And that is my answer. It's not crazy profound. It's not going to change your life to know this fact, but it's kind of cool to know that you could take these two separate f of x's and combine them together into a single f of x. If it cost you $100 every single time you wanted to pay an intern to go out and calculate something for you, it's nice that you can merge them into a single statement instead of having to pay for it twice and then subtract them, if you're in that predicament. All right, so a similar deal. We know from -2 to 8 of this function is going to produce 4, and we're going to try and find a way to use that down here. Ultimately, what I want to try and do is merge these together into this statement. I'm lucky because I notice this repeat of zeros. Those repeat of zeros, it's kind of like the transitive property, and I can just mush the two functions together. Now that these have merged, this is essentially like my c value from that last rule of definite integrals. I can merge them together, and I see obviously my answer is just 4. The only way this other way it could have played out really would be if it was -4, if for whatever reason I ended up being upside down. All right, so the same deal. I know that the integral of this is 10, and I have to try and find this in this problem. Well, this 3x looks an awful lot like that. It's just times 3. I can actually pull that out in front of my integral, and then I'm left with the same thing. I know this whole statement is 10 by the definition up top, so what I really have is 3 times 10. And that's my answer. All right, if you want to go formal, if you're planning on taking this again in college, this might be the way that your college professor throws it at you. It's a very intimidating problem, and quite frankly, I don't have enough time on my screencast to be able to do this. I might need 10 minutes just to work this out for you in the next example, but I want to give you an overview. Basically what this is saying is if you have this function, this definite integral from a to b of f of x, it's essentially asking you to calculate a limit, this is why we learned them way back in chapter 2, as n approaches infinity. You can't literally have an infinite number of rectangles because that's not conceivable. But what you can do is try and get as many rectangles as you could humanly conceive. So try to come up to this idea as n approaches infinity. We can't have infinity, but we can approach infinity. Sigma means sum them up. So I want to add up all these rectangles, all these n rectangles, and I want the area of each rectangle. How do I compute the area of each rectangle? I take the width of the rectangle, this delta x that we calculate, times plugging this x sub I into the function. If you were actually to do a RAM by hand, then each time you would calculate the y value of the coordinate so that you could figure out the area of the rectangle. This is the width of each rectangle, and this is how I calculate the y value. That x sub I, assuming we go, let's say, left hand, is just going to be a plus however many rectangles I've used times delta x, assuming that we're going LRAM. That's my formula for x sub I. So we can plug that into the function and then go from there. It requires you to be pretty good at sigmas. You've got to know some formulas for the sum of the first n numbers to be able to make this really work, but more often than that's going to be more of a college thing than our high school honors calc. So hopefully definite integrals make a little bit sense, and hopefully you're not going to have too bad of a time with the homework. All right, see you soon.